First of all, thank you all for coming, and thank the organizers for having me give this talk. I should say that before I start, is that my background is my background is actually kind of more in kind of combinatorial algorithms, but then at some point I kind of learned some optimization for reasons that I'll try to describe. And one of the reasons was just for some of these problems that we would like to solve, it's just very hard to get very good approximations. So plan for the talk is I will motivate things via the network flow problem. And then in the first half, I'll talk a little bit about generic optimization algorithms and how optimization algorithms work. And hopefully by the break, I'll get to inverse maintenance, so how to maintain the, so how to maintain the solution of a system of linear equations where the weights are continuously changing. And then in the second half, I'll talk about how to do some of these things on graphs. So let me start with a motivating problem, which is a problem that we're probably all seeing in some form or another, which is I have a graph, I have a S and T, and I want to ask to find the maximum number of edge disjoint paths. So this problem, this is kind of one of the simplest way I like to say why these things are optimization, is that instead of saying finding one path, so instead of checking whether there exists a path, or instead of say counting the number of paths, I'm asking to find the maximum number. It's essentially a packing problem. I'm trying to fit the most number of edge disjoint paths into the problem. And algorithms for this kind of problem have a very kind of strange flavor in that it's the type of algorithm where if you do the wrong thing enough times, they will give you the right answer. So let me start with the wrong algorithm, which is I just find a path, remove it. So this is kind of like the classic greedy algorithm. And this is incorrect, right? So what you can have is that in the graph up there, I found that green path, I removed it. Now S and T is disconnected in the resulting graph. I've just disconnected S from T, even though there really are two edge disjoint paths. So optimization algorithms are in some sense kind of, I mean, almost in some way, actually, here's a funny thing. Because this is a small enough crowd. How many have seen this paper called Incorrect Versions of Floyd-Warshall Converges After 3 Iterations? Okay, so some have seen this. There's this great thing on arXiv which says that, so is everyone familiar with the Floyd-Warshall algorithm for shortest path? It's just like 3 nested loops that's just kind of magical. And somebody wrote a paper that says that if I get the order of those 3 loops wrong, no matter how I get it wrong, all I have to do is just run the algorithm 3 times, and the answer will be correct. Optimization algorithms, in some sense, are kind of a more kind of systematic treatment of such a phenomenon. In that, what you say is that, hey, once I took an edge in the forward direction, so the kind of the key thing is you allow yourself some kind of regret. So you say that, hey, if I took an edge in the wrong direction, so if I took an edge, so here I took the edge from kind of the bottom to the up direction, the middle edge, what I do is I say that, hey, if I undo it, what is that equivalent to? That is equivalent to me routing 1 unit of flow in the opposite direction. So what you create is kind of the key thing to optimization problems are these kind of residual instances, which is you kind of make an instance which represents what kind of progress can be made in this graph. So here what you do is you take the edge, you flip it around, and you say, hey, is there a path in this new graph? And here you do have a new path, because now you can go up, and you can take the edge in the opposite direction, and you can end up at T. So you end up with this other path. And once you sum together these paths, what happens is that this middle edge, so the top path uses it once in the kind of the upward direction. That way in the middle there, it's using it once in the downward direction. So once I send flows in both directions along an edge, they cancel. And once you get that kind of cancellation, you basically it just undoes itself. So the way you can think about this is that this is kind of, I mean, I think the way I've heard this style of algorithm best described is that this is exactly not the stuff you want to teach in undergrad algorithms, especially introduction to undergrad algorithms. Because what it's really saying is that if I modify my greedy and I kind of iterate on it, it will actually get the right answer sometimes. So, there's a kind of a lot of very interesting work on proving the convergence of this. Unfortunately, that's a whole another discussion of like how to prove this type of convergence. There's actually there's kind of a lot of invariants, potential functions. There's a lot of very beautiful work. High-dimensional geometry comes in. I want to kind of focus more on kind of the efficiency issues that come out of this. So the issue now is that I just took a very simple algorithm, which is pathfinding. But now I need to run this repeatedly. So the potential issue now is that I can get a graph, first of all, where there's a lot of path. So it's possible that I need to take at least n of these paths. At the same time, my graph could have very large diameter. So each of these paths could actually be as large as n. Multiplying these two together, you get a quadratic time algorithm, which I think from both, well, it used to be from kind of a more kind of a theoretical perspective, but I think with these days, I think networks with, say, a million to a billion edges are very common. Like Snap has a ton of networks that basically takes about a day to download. They're somewhere in like the 80 to 100 gig range. So you get a lot of large graphs. And then there's a very natural question in all of this, which is how do I make these things more efficient? And as Cyan and Thatcherpool mentioned, studying this phenomenon is kind of, it dates way back. So there's actually kind of well, there's two things you can do to this kind of stuff. One is that you prove better iteration counts. So by like getting better kind of iterative algorithms, you can decrease the iteration count. So on a general capacitated graph, the one I just talked about is something like, I think it's something like total amount of flow, so total capacity iterations. You can get this down to something like n times m, and then kind of the more recent stuff do about square root of m iterations. There's another line of work that is kind of interesting here, which is that if I have a path, this is from Galileo and Namad, and what they showed is that if I have a paths are basically binary search trees, right? Like we are very good at maintaining lists using dynamic search trees. So maybe we can just compress the path. So their idea was they developed basically splittable path things, but then they observed that inside these algorithms, what you get is not just path. What you actually get is you get trees. So what they ended up doing is that they ended up having some kind of tree decomposition. Took a tree, turned it into a bunch of paths, and then maintained the path using balanced binary search trees. And this was known as dynamic trees, and this is actually kind of the precursor to the linked trees line of work, which actually got it's kind of the right answer for this problem. So Galileo Namad was like log squared n. There's a couple other log squared n. I think then there was a log n, and there's actually, we know a whole bunch of ways to get to log n. But what this is saying is that in like optimization algorithms, there's this kind of tension between these two things, which is that you either want to decrease the iteration count, or you want to speed up the cost per iteration. And the goal is you want to have the product of these come out to be ideally m instead of n times m. So to give another example for this, why does shortest path work? You can prove that if there are k units of flow that you could still send in the graph, because these k units are edges disjoint. These k units of flow, there's m edges total, right? So the shortest path have length at most something like m over k. So you just get a harmonic series kind of sum. So this is kind of like the simplest intuition to like the why does dynamic shortest path give you a almost linear time max flow, which is you just sum across k from 1 to m of m over k. And that's essentially the minimal kind of size of the change you have to do. I would love to see something that kind of gets in that direction, except that kind of a lot of the more recent developments are really through what's called optimization algorithms. So the same kind of phenomenon, so roughly at around the same time as the kind of the work on dynamic and link cut trees were happening, there was also a lot of very exciting development that happened in solving linear programs. So one of kind of the surprises there was that kind of the fastest, well, the current fastest algorithm for solving linear programs are all by solving a sequence of linear systems. So this started with work by Karmakar, and then, so Karmakar said that basically to solve a linear program to accuracy epsilon, you can solve something like m log 1 over epsilon systems of linear equations. And in the same paper, actually, Karmakar also showed that these are very slow changing problems. So he actually, he was working with n-cube time matrix multiplication, because actually this slightly predates, like there were a lot of developments in matrix multiplication at that time. I think when Karmakar came out, I think it was like either 2.51 or 2.49 was omega. And then I think 2.37 came out a couple of years after that. But so the kind of the interesting, very interesting observation from Karmakar's result was that even if you use n-cube matrix multiplication, the amortized cost per iteration of his linear system is something like m to the 2.5. So once again, you have the same phenomenon, which is that you have a lot of kind of very interesting things you can do about reducing the number of iterations. And then you can also work to speed up all these iterations using dynamic data structures. And my plan is to first kind of introduce why we would want to, so I want to kind of first talk about things in the matrix setting, because just to give a kind of little more intuition of how these iterative methods work. And then I'll try to talk about what is the implication of this on graphs. But before I continue, any questions about what I've talked about so far? Okay, so let me just quickly start diving into what is a optimization algorithm. So the generic idea of optimization algorithm, actually, maybe let me have a show of hands. How many have heard gradient descent? Okay, so the quick intuition about gradient descent is that if I have a convex problem, the minimizer must have gradient 0. So assuming there's like no linear constraints on the x variable. If I have a convex problem with no linear constraints, so it's like I just minimize f of x, where f is a convex function, the calculus statements basically say that gradient must be 0 at the minimizing point. Furthermore, you can also show that if I have a gradient, so I have a gradient vector, and it's non-zero, and I take a step in the direction of the gradient, any vector dotted against itself is a positive number, right? So if I take a step in the negative direction of the gradient, so if I have gradient dotted against, oh, I should also say that for a function, if I change in some direction, the change to the value of the function, when you go infinitesimally small, is just gradient dotted against the direction of the change. So if you just take the gradient itself and you dot against your direction of change, you get roughly, you're going to get the function value is going to decrease by a negative value, with one caveat. The caveat being that the function is, the gradient is going to change. So gradient descent is basically how a lot of these algorithms, when you implement in the real world, you have like a convex function you want to minimize. So things like gradient descent, SGD, basically just take the gradient information. In terms of proving bounds, the best bounds are coming from what's called second-order methods. And what second-order methods do is they precisely try to control this issue, which is my gradient is changing. Sometimes they change the function a little bit, but the generic thing you do is you kind of normalize how much you want to change by looking at the second-order terms. So the generic idea is that if I have a convex function phi, and I want to minimize it, and I let my change be delta, a very good approximation is gi delta I plus hi delta I squared. This ends up being sufficient because you can also show that any error in, so this has several very nice properties. So the first thing is that why is it okay for us to just ignore third order, fourth order, and so on terms? The reason is that as long as delta I is reasonably small, so think of delta as like much smaller than, think of delta I trending to 0, but like not exactly 0. So think of like hi delta I squared to be like less than, say, 0.1. That's kind of the parameter regime. You can actually show that the third and higher order terms is just like within a factor 2. So by Taylor expansion, you can show that their magnitude is at most factor 2. So this approximation is actually both an upper and lower approximation, subject to a different coefficient on the quadratic term. And why is additional terms on quadratic terms okay? The reason additional kind of coefficients on quadratic term is okay is that if I take a step and I scale it down, so if I take delta and I replace by, say, delta over 10, gradient term decreases by a factor of 10. This second order term decreases by a factor of 100. So by just taking constant size steps, by just like reducing your step size by a constant factor, you're essentially able to gobble up a lot of any kind of like extra constants sitting on your higher order terms. So this ends up being like a very kind of friendly, so this is kind of the intuition why 2 terms is often enough. Subject to what's called a Hessian ball condition. And then the other thing that you can do now is that, that happens now is that if you look at the first term, this is the gi delta I term. This is gi delta I. If you look at that term, that's just a linear constraint. So the other kind of cool thing about convex functions is that you can binary search. So you think about a one-variable convex function, right? How do I get to the minimizer? I can just binary search. If I look at midpoint, see if the derivative is positive or negative. If it's positive, I go to the right of the midpoint. I go to the right of the midpoint. If it's negative, I go to the left of the midpoint. So maybe actually, if it's positive, I go left. If it's, okay, yeah. Anyways, the rough idea is that you can essentially use binary search to minimize convex functions. And the same applies if you restrict a convex function to just 2 terms. So if you take any kind of like section of a convex function, say like a one-variable section, you can just binary search on that. So what you can do here is you can actually like solve versions of this where you just like artificially restrict gi delta I to equal to some value and minimize the second term. And with that, you can also convert to the optimum, basically using some variants of binary search. So what you get there now is that you can actually minimize delta in some linear space, subject to another linear constraint, of sum of hi delta I squared. And that is a very nice problem to work with. Because this is a quadratic minimization. Quadratic minimization we know how to solve. It's just a solution to a system of linear equations. So quadratic, derivative is just linear, right? So solving derivative equal to 0, that's just solving a big system of linear equations. So that's kind of like the fullest detail, which I want to talk about kind of basically how an interior point method works. I'm going to give you kind of like the mental shortcut, by which how I like to think about them in a second. So before I kind of go to the simplified version, any questions about kind of this like attempt at talk about interior point method on one slide? Okay, so now let me give you my mental shortcut for how I like to think about this. It turns out that a lot of things for modern interior point method, you can kind of visualize them via this paper, this algorithm given in the paper by Cristiano Connor, Madri, Spielman, 10, which was the first kind of numerically based improvements on network flow, and this was STOC'22. So the idea is that I just think in terms of multiply weight update. And what happens is I assume that there exists some x star, such that ax star minus b is entry-wise less or equal to 1. So basically, the way to think about it is that I want to search for a point where the point is less or equal to 1 everywhere. And if I do have such a point, what is that point going to satisfy? That point is going to satisfy that for any set of weights that I could generate, for any set of these wi's that I could put on the entries, I'm going to have that wi yi squared, because yi squared is at most 1. It's going to less or equal to the sum of the w's. So what you can show is that for any set of weights, the key is the any set of weights, w, the minimizer of wi ax minus bi squared is less or equal to the sum of the wi's. And this is precisely the condition you have from, say, regret minimization. This is the kind of stuff that lets you run regret minimization type algorithms. Those familiar with regret minimization, there's one more condition you need, which you need to control the width. This is kind of where you pad the wi's a little bit. You like artificially pad the wi's with the sum so that to make sure that none of the terms themselves gets too big. And then all you do is you just iterate. You just take a step of size alpha, and you just do ax minus bi squared, and you just multiply the w's by that. So you get a multiplicative weight update, where each iteration you're just changing the wi's. And if you pad, so there's some padding that I'm ignoring here. But the kind of the standard way to pad is you just add the average of the w's to everybody. And this is a much nicer one to think about for a whole bunch of reasons. One being that the w's are monotonic. The other one being that, so first of all, the w's are monotonic. Secondly, it's kind of robust to errors. So you can just always pretend that the wi's only change something like log n times. So from this one, assuming everything's polybounded, you can just immediately get that the total amount of change to all the w's is something like m log n. So it's actually not a very large number of changes where all these weights are happening. And from this, you see that basically the solution to optimization problems is just put together the solutions to a bunch of iteratively changing systems of linear equations. There's also one other thing with this, is that if you can also, this is also a setting where it's actually kind of easiest to kind of analyze these things to a smaller iteration count. In fact, kind of the key idea in the Cristiano et al. Paper is that they got the iteration count down to m to the 1/3 instead of square root of m. So there's actually another potential function involved. I highly, if you want to kind of understand like kind of how to analyze an optimization algorithm and open up an optimization algorithm, I really recommend this paper because it kind of like isolates away a lot of the kind of the details that kind of makes interior point method very hard to work with. Any questions about this model? Okay, so hopefully I've isolated the problem by now. It's that I basically have a sequence of wi's that are changing. And I want to repeatedly compute the minimum x that minimizes sum of wi ax minus bi squared. So there's a system of linear equations where I'm repeatedly changing the weights of the elements. And here there's kind of an important thing, which is you think in terms of linear algebra. There's this formula called the Woodbury formula, whose details, I really don't like to write down the Woodbury formula. But the way to remember the Woodbury formula is that if I take a matrix and I make a rank R change to it, its inverse also changes by rank R. And this fact is kind of, this fact is really just coming from the rank of a matrix equals to the rank of its inverse. But Woodbury is basically the kind of the numerical version of this. It basically expresses what that change is as to the change of the original matrix. Of course, the problem is that if all the changes are rank 1, that's actually not very good, right? Because every edge's weight is changing something like log n times. So potentially, so if you kind of directly do the analysis without coupling the optimization algorithm and the data structure, a kind of a back of the envelope calculation gives you that you're doing something like m updates of rank 1 to a problem. There is one thing that really helps a lot, though, which is that the total number of iterations is only square root of m. So what is kind of like, so where do we start getting gains? We are actually getting gains from the fact that a lot of the changes are happening together. They're happening in a very batched manner. So, I mean, here I'm going to resort to convexity because I've been saying convexity for a while. So usually when you get this kind of functions, you want to check a couple of things. Well, these days what you want to do is you go to Jan van den Brand's website, and he has a program that essentially lets you kind of optimize the coefficients of a matrix-based formula. Oh, yes. Inverse or pseudo-inverse? Oh, okay, the question is inverse or pseudo-inverse. Oh, so these problems, they're all happening in the weakly Pauli regime. So there's always some kind of bound that, so basically like once you're at one of these kind of like descent kind of algorithm, I mean, it's binary search, right? So binary search, I mean, you're not given, like, I mean, it's a very nice question to see like whether you can actually get like the simplicial point or something like that. I'm actually ignoring all that issue. So basically the way that you avoid pseudo-inverse once you work in the weakly Pauli regime is you just pad everything with a very small copy of identity. You just add like epsilon times machine, like you just add a machine epsilon times identity to everything. Okay. And now you're working with kind of inverses. But yeah, no, the pseudo-inverse kind of questions, that's also, yeah. That's actually kind of very interesting because you actually, like, one of the things that actually makes it so hard to define like hardness for these things is like how do you define these things on integers and still be able to properly deal with pseudo-inverses? That's actually very complicated. Yes? Yeah. Yeah, exactly. So one thing that I was hiding in this kind of intuition on the previous slide is that this does not give you high accuracy linear programs. All this is going to give you it's not even going to solve your linear programs. What it solves regression problems. So you're trying to minimize some norm subject to a linear constraint. And yes, like basically the algorithm, like basically once you want to actually get high accuracy, it's actually a significantly different algorithm. But that's actually kind of the reason I like to kind of think first in this framework, because somehow by some very bizarre kind of thing, like this algorithm somehow gives you kind of like the most optimistic sequence of updates that you ever have to make. Like it kind of gives you like, if I get the algorithm, if I do like basically everything that I want to do to an optimization algorithm, what is the runtime I get? So somehow like to kind of do the first step. So because I mean the issue with working on all this stuff, right, is first you work on the optimization algorithm and then you kind of think like, what is the data structure I need? So you go like, what is the minimum my data structure needs? And then somehow in these matrix settings, it's actually very useful to kind of go to this algorithm. I mean, you can even use the 1/3, but I mean, you can, that 1/3 transferring that over to the high accuracy setting, that's a huge open problem by itself. Yeah, I think we're getting to like, this is getting to like some of kind of like the intricacy and like, I mean, I would almost call it like the scariness of this field, in that like, if there does happen to be a change on the iteration count, like the trade-offs on the data structure side is also going to change. And somehow like this algorithm kind of actually makes it very clear like what are the potential things that need to happen. Like if the iteration count is something, your data structure needs to do this. If the iteration count is this, the data structure needs to do this. Okay. But I guess we're coming up to the break, so let me just quickly point you to this website and then say that basically the bound that you could plug in is you just say that instead of doing m rank 1 updates, you do square root m updates of rank square root of m. And then out comes this bound that comes to roughly about m to the 2.54. You can actually do even better than this. To do even better than this, what you say is that so it turns out that if I have root m batches of things, those are all rank 1. And when do I get to root root m size batches, I only need to deal with root m size batches, something like every m to a quarter iterations. So there's actually kind of a further trade-off of like, how often do you get batches of a certain size? You get like, I think there's like a polylog times you get batches of size m as well. But for that, you just rebuild. So there's actually like a further trade-off that you do here to like basically get kind of you can actually recover into the omega. Or like, I think you can recover to 2.5 at least with this. And then there's some further tricks you do to recover omega type things. But the point is like, this is kind of like what I like to think of as kind of like the optimization plus data structure on 2 slides. In that on one slide, I tell you here are the weights that are changing. And then the next thing you do is, oh, like it's a rank something update to the matrix. What if I just go update the inverse? What do I get? And then basically I claim that like a lot of the other kind of things are kind of like doing this for a better optimization algorithm and doing this for a harder data structure problem. Yeah, I mean, basically, so this is basically what like a lot of the recent results were doing. So you can decrease the iteration count. You can also decrease the cost per iteration. So Vijay got to 2.5. And then there's this remarkable paper from a couple years ago by Cohen, Lee, and Song, who introduced robust central path, and they got it all the way down to m to the omega as well. So that one's actually, it's very interesting in that the iteration count itself is still square root of m, but it's avoiding looking at the inverse entirely every step. I think this is what Yang will talk more about in his talk. Yeah, let me. Yeah, so let me. I think I'm already over time for the break, but I just want to say that there's like actually here there's actually for this kind of for the matrix setting, I actually work kind of more on like kind of the optimization side. So I just want to mention that there are some potential things in the matrix side that actually could change things quite a bit, which is there like more general notions of preconditioning? Is it possible to further take advantage of sparsity? And then this is kind of the question I think Amory was asking is like, what happens if the iteration count is like something like 1/3 instead of 1/2? Like what happens to things in like as we go into that regime of things? And that one with sparsity can also change things up quite a bit. So I think I can take questions offline. We're heading to the break, and after the break, I'll talk about the graph theoretic versions of these things.